Alright, I'm going to do example 15.10. So in this system we have a mass hanging from an elastic cord from the ceiling. So this thing right here is stretchy. The ball itself, or the ball and the ceiling itself, have a coefficient of restitution. So what's going to happen here is we're going to pull down the mass stretching the string an additional 0.25 meters, and we're going to release it, and it's going to fly up with some velocity, smack the ceiling, come back down right after the collision with a new velocity, and return to some other position, but probably not quite as far as it was before, right? So maybe 1.2 meters? I don't know, that's just a guess. The equilibrium position, or the unstretched length of the string, is 1 meters. Alright, so we're given it's stretched 0.25 meters and released. We're given the coefficient of restitution is 0.8 when it hits the ceiling, and we have the mass of the ball. We're going to pull it down 0.25 meters from the equilibrium position, let it fly up, smack the ceiling where a collision occurs, bounce back with a different velocity due to E, and stretch the elastic cord some new amount in delta x. And that's what we want to find, is what is the new stretch. Before it was 1.25 meters. Well, it shouldn't make it all the way back down that far. It should be a little bit less. So let's figure out. In that case, the delta x was 0.25 meters. What's our new delta x on when it comes back down? So I'm going to go ahead and find out how fast that thing is going right before it smacks the ceiling. So let's do a conservation of energy. T1 plus V1 is equal to T2 plus V2. It's released from rest, so it has no kinetic energy. Depends what we call our datum in this case, right? So let's go ahead and call our datum y is equal to 0 right here. The book does it a little bit different, I believe. Alright, that means we have no potential, alright, gravitational potential, but we do have some spring potential, 1/2 kx squared, where that x is the 0.25 meters. This is all going to turn into some kinetic energy, and we'll call this our V2 right before it hits the wall. And when it gets up there, it's also going to have some potential gravitational energy. Alright, so we can say, well, we know everything actually, right? Yep, we can solve this for V2. V2 ends up being 2.968 meters per second, and that's right before it smacks the ceiling. Okay, hold on to that number, and the next thing we need to do is figure out how fast it. So if that was how fast the ball was going right before it hit, it's going to deform, and then it's going to bounce back the other way. So they gave us E as 0.8, the coefficient of restitution. Let's see what we can do with that. So 0.8 is equal to, I'm going to write out the whole formula, the velocity of B at 2 minus the velocity of A at 2, all divided by the velocity of A at 1 minus the velocity of B at 1. We're talking about the ceiling, which is not moving. It's basically the Earth, right? It does move a little bit, but not measurable. So I'm going to call that our velocity b and cancel those. And we'll get a relationship that says kind of like in our previous example, that the velocity after the collision is going to be equal to the scaling factor, the coefficient of restitution, times the velocity it hit the wall with. And we're going to throw a minus sign on there because it's going to be coming back the other way. So just 0.8 times the velocity we found earlier, we get the velocity of A at 2 to be negative 2.374 meters per second. And that's right when it's bouncing back down. The 2.968 was right before it hit the ceiling. Okay, they want to know how much the string or elastic cable is going to stretch after it moves back on its way back down. So it has some velocity as it leaves the ceiling, and it's going to cause us to go past the equilibrium position of 1 meter, some extra delta x. Well, that's what they want us to find. So let's conserve energy again. I'm going to say T1 plus V1 is equal to T2 plus V2. We know that it's got some kinetic energy, 1/2 mv squared, right when it leaves the ceiling. When it is up at the ceiling, we called this y equals 0 at its unstretched length, and that would give us an mgh where h is 1 meter. All of that is going to turn into, I'm about to cross it out, but I usually write it anyways. The velocity here is going to come to 0 when it's at its final stretch, so we can cross that whole term out. All of the energy is turning into some 1/2 kx squared. I'm going to leave that blank for a second because I'm going to put the same term in for the potential. Now, I don't normally do a negative potential term. I would throw that on the other side to keep the minus sign away. But we're coming down, if this is y is equal to 0, we're going in the negative direction, some negative x. So we're going to get a negative contribution to our gravitational potential energy, and I'm going to put a negative x in for that. So you'll see for the spring term that does not matter, but we do need that negative sign right here. Okay, we can, we have numbers for everything except for x squared and x. It looks like we have a quadratic in x. So solve that any of your preferred method, quadratic formula, and we should get an x equal to 0.237 meters. That's versus the 0.25 meters it was stretched initially. So, like we predicted, it didn't quite stretch as much. That was because E was equal to 0.8. If E was equal to 1, then we would have, so if E was equal to 1, then X would have come out to be 0.25 meters, just like we stretched it. Alright, thank you.